Hey everyone, welcome back, and today let's solve Leetcode problem 2563 titled Count the Number of Fair Pairs. So we're given a zero-indexed integer array nums of size n and two integers lower and upper, and we need to return the number of fair pairs. And a pair I, j or index I, index j is fair if I is strictly less than j, and they're both within bounds in the input array. What does that mean? That means they're greater than or equal to 0, and they're less, strictly less, that is, than the length of our input array nums, which is n. And we see that another criteria that we have to meet is that nums at I plus nums at j, the sum of those two values in that pair has to be at least lower or greater than or equal to lower, and at most upper or less than or equal to upper. And we need to simply return the number of pairs that are fair, or in other words, meet this criteria. So in example 1, we have our input array nums to be the following of 0, 1, 7, 4, 4, 5. Note, very important, that it's not necessarily sorted. And we have our lower and upper bounds to be 3, 6, right? Or 3 and 6. And we output 6. Why is that? Because there's actually 6 fair pairs or pair of numbers that actually meet the following criteria. And note that when they actually give us these tuples of length 2, they don't give us the values themselves that are in our input array nums that actually do meet that criteria. They give us the indices that actually do. So as you can see, index 0 and index 3 of our input array nums meets this criteria. What is that? That's going to be 0 and 0, 1, 2, and 4. And so does 0 and 4, which in this case is 0 and another 4. 0 and 5 also works, which is this 0 and this actual 5, right? Okay, yeah. And then 1, 3 also works. Why? Because it's this 1 and it's this 4. 1, 4 also works because it's this 1 and this 4 is again. And 1, 5 also works because it's nums at index 1, which is 1, and nums at index 5, which is also 5. And the key thing to know about all these pairs is that they have values or a pair of values that actually have a sum that's at least 3, not less than it, and at most 6, not more than it. Right? And so for that reason, we output the value of 6. We don't care about the actual kind of indices themselves or the pairs themselves. We just simply have to output the number of fair pairs that we actually find. In example 2, we have our input array nums to be the following, and we have our lower and upper bounds to be the same thing. So in other words, we simply just have to find how many pairs actually sum up to that lower bound, right? Because, or rather even upper bound, because they're equal. Right? We don't have too much space to actually kind of move with. So there's a single fair pair in that case is going to be index 2 and index 3. Why is that? We can take this 9 and this 2. 9 plus 2 is 11. 11 is actually less than or equal to 11 and also greater than or equal to 11. And so for that reason, there's only one single fair pair we can do to make up 11 in this case, which is both our lower and upper bound for that kind of range to look for, right? And keyword being range to look for. That kind of highlights or hints an algorithm. I won't leak it now, but I will kind of just tell you guys how I'd solve it in a few seconds. Okay, so if you guys haven't got the kind of algorithm used already, we're going to use binary search, and the way we're going to structure this is, note that our input array nums isn't actually given to us sorted. It's not originally sorted, and to use binary search, we have to have a sorted array. Otherwise, it literally is completely false. It does not work. And so we're going to actually first sort the array to, again, easily use that binary search algorithm to actually find the range of different indices that we can form valid pairs with. Or in other words, the range of indices that have a sum less than or equal to lower, but also greater than or equal to upper, right? Basically, the range of indices that actually could potentially form valid pairs, right? And for the binary search for those bounds, for each element, nums at index I, we're going to use binary search to find the range of values in nums at index I plus 1 up until the end of the array that sum with nums at index I to fall between those lower and upper boundaries, right? To actually have a sum within those actual parameters, right? And we simply have to just count all the valid pairs that actually do fit within these bounds, all the number of fair pairs, and return that value. Okay, so let me just delete this real quick. We'll go back to that example later. I just kind of coded it up for you guys to share with it. I'm just going to comment this out. We'll go back to this later. Okay, so the first thing that I'm going to do is actually just quickly import a module. So I'm just going to go to the first line of code, and I'm going to say from bisect in Python, I'm actually going to import, I'm going to import the bisect left and I'm going to import the bisect right methods, right? Quick thing here, bisect is simply a module that we're importing two different features of it from, right? What do they actually do? Why do we actually need it for this binary search algorithm? Well, quick rundown of a high-level rundown of what these do. Bisect left is simply just going to find the insertion position for a value in a sorted array, and that's going to actually give us the first index where that value could actually fit. And bisect right, pretty self-explanatory, also does find that insertion position, but it returns the position one index after the last occurrence of that value, right, where we would insert it to the last, to the right of it, okay? That's just a quick high-level rundown. Okay, so now that we have that, now let's actually go into the actual sorting. So nums.sort in Python to actually enable us to use that binary search algorithm to look for the different ranges of indices or bounds of indices to actually be fair pairs or form fair pairs, right? To actually allow us to use binary search to find those different ranges quickly and efficiently, right? That's the main part, right? Okay. So now that we've actually sorted the array, I'm going to initialize my count, and I'm just going to initialize it to be 0. What does this count do? It's simply going to store or hold the number of fair pairs that we actually find that satisfy the conditions, again, defined by these lower and upper boundaries, right? It's simply going to be the value that we return after we traverse through the entire input array. But before that, we also want to do one more thing here. Oops. We also want to make sure that we actually get the length of our input array nums just for easy access later on, because I don't want to type length of nums continuously over and over again. So I'm just going to store the length of our input array nums into a variable called n, pretty short, and set it equal to length of nums. Okay, so now that we've done that, now let's actually just loop through that value. So for I in the range of n, again, note that that's just length of our input array nums, right? We're just basically for index I, we're just iterating through each element in our input array nums, and basically to just examine each element that actually we can use to find a valid pair where that index I is less than our index j, right? That's what this outer loop is basically doing. So now that we've actually initialized our for loop here, now we want to actually get the left boundary of our valid pair now that we've sorted it. So I'm going to initialize left, and it's going to be equal to bisect left. In fact, yeah, I think it's an underscore here to actually initialize it. And we're going to have three different parameters. The first parameter is simply going to be our actual iterable. It's going to be our input array nums. Our second parameter is going to be lower minus nums at I. I'm going to explain this in a few seconds. Lower minus nums at I. I'm actually going to space that out for readability. And my last parameter is going to be I plus 1. And I'm going to do the same exact thing for my right boundary, right? It's going to be equal to bisect right, the other feature or method that we imported from our bisect left module, or rather our bisect module. And it's going to be also on our input array nums. We're going to have our other parameter to be upper minus nums at I, and we're going to finally have I plus 1 as well. Okay, let me just kind of quickly, or not quickly, pretty detailedly explain what does this do? What are these three parameters actually kind of telling us to do? Okay, so the first line right here, it's going to find the leftmost boundary of valid pairs for this current window that actually has that criteria of meeting these following bounds, right? We actually want, let me actually comment this out real quick. We actually want, we actually want nums at index I, our current iterator, plus nums at index j, like it says in the problem, to be greater than or equal to our lower parameter, right? That's literally how a fair pair is defined to be. And using some math strategically, we can actually subtract a nums at I from both sides, right? From both sides of the equation. And then we get that nums at j has to be greater than or equal to lower minus nums at I. We just subtracted a nums at I from both sides, which gives us that second parameter of lower minus nums at I, right? We want nums at j to be greater than or equal to lower minus nums at I. Why? Because that's going to give us a fair pair. That's going to give us a sum that actually is greater than or equal to lower, where nums at I plus nums at j is greater than or equal to lower. And again, what does this kind of do as a whole? What does bisect left with these three parameters work as a whole? Well, it simply just returns the first index j in our input array nums, starting from I plus 1, which is our last parameter, where nums at j is actually greater than or equal to lower minus nums at I. And that makes sure that nums at I plus nums at j is actually greater than or equal to lower for all indices j that are greater than or equal to that left index, all right, which is I plus 1. Okay, and similarly for this right variable instantiation, it's going to find the rightmost boundary of our valid pair, this current window of valid or fair pairs that we're searching the range for, right? Where we want nums at I plus nums at j to be less than or equal to upper in this case, right? Let me just comment this out as well. We want nums at I plus nums at j in this case, rather than to be greater than, to be less than or equal to nums at j. Or rather, sorry, upper, okay? And again, strategically rearranging here, we see that nums at j has to be less than or equal to upper minus nums at I, simply just subtracting nums at I from both sides of the equation again, right? We're simply looking for that nums at j that fits this criteria, which is our second parameter. And what this bisect right does as a whole, to reiterate, it returns one index to the right, or past the last occurrence of values or indices that actually fit or satisfy this condition. And so this is going to this index right is going to actually mark the upper bound of valid j values for that current index I, where again nums at index I plus nums at index j is less than or equal to upper, and j is greater than I, strictly greater than I, because we don't want a duplicate element, okay? And then once we've actually initialized these two variables, we simply have to increment to our count the size of this window. Sorry, not one, the size of the window, which can be determined by the right minus left, right? Basically the difference between these two boundary point indices for this current window. Why? Because that's going to tell us how many values in this range actually fit this criteria, actually have a sum that's greater than or equal to lower and less than or equal to upper, where j is larger than I, using these bisect left and right modules to actually get these boundary indices, right? So going back to that example here of 1, 2, 3, 5, 6, 7, right? This is after we actually sorted our input array nums. You could assume it was something else before. Now, assume left was 2 and right was 6. This has a sum of 8, okay? And all of these values, since that this is sorted in this range of 2 to 6, left minus right, or rather right minus left, are going to be all the distinct values from, not distinct values, but rather all the values from distinct indices that have a sum that's less than or equal to upper and greater than or equal to lower. 2 plus 6, well, that's 8. 3 plus 5 is also 8. 2 plus 3 is 5. 3 plus 5 is 8. And 3 plus 6 is 9. Assuming, I don't know, lower is like 8 and upper is 9. Doesn't really matter here. Rather, lower is 5 and upper is 9. If we had those two parameters, this range would actually work. And that's why right minus left would give us the number of distinct values that we can actually add or count to. Because again, count is going to store the number of fair pairs of values from different indices that meet this following sum criteria. And right minus left, the two boundary points of our current range of indices that meet this criteria, because again, we sorted our input array nums, is going to tell us the number of values in this range of left to right that actually fit this criteria, having a sum that's within the bound of lower and upper, and also having j greater than or equal to I, rather just simply greater than I, our two indices for this current range, right? It's going to, again, give us the count of indices j in the range left-right, which satisfy both the conditions, and we accumulate or add that value to our count variable. And effectively, once this for loop is done, once we've iterated through all the indices or elements at index I in our input array nums and checked for the values in the corresponding ranges to meet this criteria, then we can simply return our count variable. Why? Because that would have actually stored the final count of all the valid or fair pairs in our input array nums, which is actually the solution to our problem. So unless I made any syntax errors here, this should be accepted and this should be a valid solution. Okay, let's see what I did wrong here. Okay, find the range n. Oh, oops, I returned count right here. Sorry about that. Now this should work. Sorry about that, I returned count two times. But as you can see, if I were to submit this right now, this would actually be a valid solution. Okay, let's see here. Okay, this should be yeah, this should be lower. I don't know why I have lowers there. But now this should work. Sorry for the syntax errors, you guys. Just me kind of fat fingering my keyboard. But as you can see, this is just about as efficient as you can get it to be, right? So to kind of reiterate, what does this code do overall? We're simply first sorting our input array nums to actually enable us to use our binary search algorithm and initializing this count to be 0 to store the number of fair pairs in our input array nums. And we're using binary search to find the range of elements using the bisect left and bisect right modules in nums starting from index I plus 1 up until the end of the array that form valid pairs with nums at I under the given lower and upper bound kind of conditions. And by counting pairs in this range for each element, nums at I, we actually efficiently get the total number of valid pairs without actually having to check each pair explicitly, right? It's a lot more efficient than having kind of nested loops, right? And so sorting is going to be actually a big O of n log n operation, and so the overall time complexity is going to be big O of n log n. And although yes, for the binary search and pair counting for each element nums at index I, binary search operations bisect left and bisect right are actually both pretty efficient, being big O of log n. And since we do this for each of the n elements, that part is also going to be big O of n log n anyways, because we actually have to iterate through all the elements in our infinite array nums, which is already a linear time solution, and when you multiply that by log n, you get n log n, and so the overall time complexity is going to be big O of n log n for that sorting and for that binary search in the linear scan of our elements. And for the space complexity, this is going to be big O of 1. It's a constant time solution. Why? Because we really only use some extra integer variables, right? Like count left and right. We don't actually use any auxiliary memory or any data structures to store any valid elements to actually count the elements from our input, and so this is going to be a constant time solution. We're not using any extra data structures that grow with our size of our input, and so this is going to be a big O of 1 memory complexity. And if you guys are interested, I'm actually going to give you the brute force solution. I probably should have done this at the beginning of the video. That's my bad. But just a quick brute force solution to kind of understand how this problem works and what it's really asking. The way this would work is for I in the range of the length of our input array nums. Okay, I think I forgot a parenthesis. And then for j in the range of I plus 1 to get that duplicate value till the length of our input array nums. First of all, we have to actually have a big base case here. If nums at index I plus nums at index j, if that's actually greater than or equal to lower, and that same value is also less than or equal to upper, then, only then, we can increment our count by 1 and effectively return that count. And sorry, I forgot to actually instantiate that count. Let me just do that right here. So yeah, this would actually, it wouldn't work. We'd actually get a TLE, a time limit exceeded, because this is a big O of n squared operation, which is actually notably slower than n log n. So we probably would pass like 40 cases, I'd assume. Just wait for this. So we get a time limit exceeded, as you can see. We actually passed 47 cases, but as for the last like 7 very large inputs, n squared wouldn't work. It'd be way too slow. It'd kill our memory's RAM. We don't want to do that. It'd take too much, RAM. It'd kill our CPU because it would take way too many operations. It'd be way too slow. It'd actually be more time than we are allowed to use. And so for that reason, we get a time limit exceeded. But yeah, this is kind of the brute force solution to really understand what this problem really asks and how it really works. Just a quick kind of high-level rundown of what the problem really asks us to do. But anyways, if you guys enjoyed this solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.